Today I'll be teaching you allosteric regulation of enzymes. Now what is allosterism? Allosteric means something which is a spatial, which is steric. The word steric comes from space. The steric means some molecules, some ligands which by binding to the enzyme is regulating the enzyme. So allosteric regulation of enzyme means the enzyme will bind to some allosteric regulators, and these regulators will regulate the will sometimes inhibit, will sometimes stimulate the enzymatic action. We know that enzymes have two parameters. One is the velocity and the other is the affinity of binding, which is reflected by the km of the enzyme. The velocity is called V, and the affinity of binding is reflected by the km of enzyme. So these parameters, the velocity of the enzyme action or the km, increases or decreases. So we know that the velocity, if the velocity increases, that means the catalysis is more. If when the km increases, then that means the binding of the substrate with the enzyme is increased. The km value is actually indicative of the binding or the affinity of the enzyme towards its substrate. Now what is sigmoid shape? What is this sigmoid shape? First I'll go into this. The allosteric regulation, in allosteric regulation there is a change in the kinetic shape, the kinetic parameters. So when I taught you about this Michaelis-Menten and hyperbolic kinetics. So hyperbolic kinetics, the shape was like this. It was like this. It was like this. But now in case of sigmoid kinetics, the shape progressively changes to a kind of S shape of the sigmoid curve. This is the S shape that I have drawn here. Now, so what is this change? Why is this hyperbolic kinetics? What is the significance of this change? The hyperbolic kinetics of the Michaelis-Menten equation, the Michaelis-Menten kinetics, now changing to sigmoid kinetics. Why is it that? And what is the significance of this change of shape? This is the progressive change of the shape that I have drawn here. See, so any curve, say I fix one curve, say this one. If I fix this one, it has a curve right, left to it. This is the left one, and this is right one. So compared to this curve. So here, if I compare this, if I take this as a standard and compare the right curve and the left curve, so what happens here? What is the difference between these two curves, towards the left and towards the right? Here in the left curve, you see the substrate concentration, the change in substrate concentration. Say this is the change in substrate concentration. Here the substrate concentration is 0. Here maybe it is say 2 millimole. Here it is say 4 millimole. The 4 millimole. So the change in substrate concentration 2 to 4 millimole is so the change in substrate concentration here to here. So here the velocity is in 2 millimoles, the velocity is this, and the substrate concentration, another change of 2 millimole, another increase of substrate concentration to 2 millimole, increase the velocity here. So there is a high increase in velocity. But here you see, for this curve, for this enzyme, so for this enzyme, here the substrate concentration has the substrate with 2 millimole substrate concentration in this curve. The velocity is here. With 2 millimole substrate concentration, the velocity is here. So it has not risen. So the substrate concentration has failed. The increase in substrate concentration has failed to increase the velocity of the reaction. So if the curve shifts to the right, the substrate concentration does not affect the initial velocity. The initial velocities are these velocities, and these are the final velocities. When the velocities go up, the Vmax, this is a line of Vmax. So the initial velocities, so there is a sluggish rise, there is a very low rise of velocity with substrate concentration as the curve shifts to the right. But when the curve shifts to the left, very little substrate concentration. Say this is the substrate concentration, and the change in just half of, say 1 millimole, this is 1 millimole, this is 2 millimole, this is 3 millimole, this is 4 millimole. Just from 1 to 2 millimole you have high increase in velocity. From 3 to 4 millimole you have another 2 to 3 millimole you have another huge rise in velocity. So the velocity rise in lower substrate concentrations are much steeper. The velocity rise at much lower concentrations. The velocity is increasing more and more very steeply at lower substrate concentrations. So this is the significance of, say, this flatness, the initial flatness of the sigmoid shape. This is the sigmoid shape, the S shape, the sigmoid shape. Why this is the sigmoid shape? This is the sigmoid shape. So this is the significance, that when the sigmoid shape is attained, there is a sluggish rise in the, there is very little rise in the velocity with substrate concentration initially, but later as the substrate concentration rises, there will be a positive kind of cooperativity, there will be a positive cooperativity. Now what does this mean by positive cooperativity? It means some kind of substrate favoring the action of the enzyme. So here, so for this sigmoid shape, let us see that here the substrate has somehow stimulated. From here to here there is this is the steep portion, the climbing portion of the curve, This is the initial flat portion of the curve, this is the climbing portion of the curve. Though this climbing portion of the curve is reached at higher substrate concentration, say here. So this here in this substrate concentration range, for this curve, the climbing concentration is the climbing part of the velocity is reached here. And this means that the substrate has somehow influenced the enzyme to increase its velocity at a much higher pace, at a much higher rate. The substrate has influenced the enzyme to increase its velocity at a much higher pace, because this little substrate concentration has produced this huge change of velocity, this amount change in velocity. But in this portion there is little bit change of velocity. There is a very little change of velocity. See, from here to here, this little change of velocity, this velocity change, because in y-axis you have plotted velocity, and this substrate concentration has changed a little. In spite of this amount of substrate concentration rise, the velocity changes so little. But if we compare the curves to the left, we see that these climbing portions are reached at a much lower substrate concentrations. These climbing portions of the curve are reached at much lower substrate concentration. Here it is absolutely hyperbolic, and here it is the sigmoid shape. So this is the change while we shift away from hyperbolic equation to allosteric regulation, from the hyperbolic Michaelis-Menten curve to allosteric enzymes. These allosteric enzymes are actually influenced by modulators. They are influenced by modulators. The modulators activate the enzyme. Some modulators inhibit the enzyme. So these allosteric enzymes are modulated, means they are influenced. So how they are influenced? There are two different models. These models are, the first model is indirect concerted actions of monode. This is the model that monode has proposed, and another one is induced fit actions, which is of Koshland's. Now, indirect concerted actions, what does that mean? Indirect concerted actions means I will explain the model of monode, indirect concerted actions. So what is that? So say there are this model proposes that there are two different forms of the enzyme, the R form, which is the active form, and the T form, which is maybe the inactive form. Now these two forms bind. This R form binds the substrate, and this T form binds the inhibitor. So there are two forms of this enzyme. This indirect concerted action model, which was proposed by Monod, says that there are two forms of this enzyme, these forms are free forms, the R form and the T form. They will bind to substrate and form the bound forms, the RS, the RS complex, and the inhibitor and the this is the form of the enzyme which binds to the inhibitor, and this is the form of the enzyme which binds to the substrate. So they will bind, and they will together form the two forms. Now if this substrate binds more than the inhibitor which binds the T form, if the substrate binds more to the R form, then this bound form is somehow more the bound form has increased this concentration. Because this bound form has increased this concentration, the free form of R has is now decreased, and these free forms, these two forms are actually reversible. They can change. These two forms can change. If this free form is decreased, this form, this T inactivated form, gets converted to R form. So more the substrate binds and forms Rx complex, this T form gets converted to the R form, and it will help bind more substrate. So there is a positive cooperativity in this way. Say on the reverse, if an inhibitor binds to the T form and forms the complex of the inhibitor with the T form, the R form will convert reversibly, because these two forms are interchangeable, because these two forms are reversible. More R forms will be getting converted to T forms, and the reaction will be inhibited. So this is the basis of the indirect concerted actions of monod. The other model is induced fit actions. Induced fit actions, this is induced fit model, or this is the model of Koshland, which says that when an allosteric regulation of enzyme takes place, there are 3D conformational changes in the enzyme. Instead of having two different forms of enzyme which binds to activators and inhibitors, here this model proposes there are different three-dimensional conformational changes in the enzyme. The conformational changes, there are structural changes in the enzyme. Say I have a structural change. I sit on the chair, and that helps me to eat food from the dining table. So this structural change has influenced my eating. My function is eating. If I stand, I will not be able to eat or hold the plate or I will not be that much comfortable to eat. So if I sit, so this is a structural change, a conformational change of my body, which has given me the ability to eat food much easier. So this is a kind of three-dimensional change in my body. Just like that, enzymes change their three-dimensional forms, and these changing of their forms it helps this changing of the three-dimensional forms helps them to bind more substrates progressively. So every substrate binding to the enzyme will get converted into a different three-dimensional form, so that its activity, its affinity towards the substrate, its activity, its velocity increases progressively, and so the enzyme gets activated. And reversibly, if it binds to the inhibitor, it will get more and more inhibited by the change in their three-dimensional forms, by changes in their conformational changes of the enzyme. These conformational changes will inhibit the enzyme. So this is the basis of allosteric regulation of enzyme. Sigmoid, say this is the sigmoid curve, the S-shaped curve, and this sigmoid curve is on the contrary, to the right is a hyperbolic kinetics. The hyperbolic kinetics of Michaelis-Menten equation. So the Michaelis-Menten equation is this equation: V0 equal to Vmax S Km plus S. So this is the equation of Michaelis-Menten: V0 equal to Vmax into S into substrate concentration by Km plus S, substrate concentration, molar concentration of substrate, where this is the, if we plot the V0 against substrate concentration, we obtain the hyperbolic kinetics. And the sigmoid kinetics, the sigmoid kinetics is given by Hill equation, and this is the Hill equation. And this is the Hill equation, where V0 equal to Vmax S to the power n by K prime S to the power n. The two reactions are similar, but there is a power, there is a power 2s. This n is the power 2s, which is called the Hill coefficient. This n, s to the power n, and k is written here as k prime of the Hill equation is equivalent to km of the Michaelis-Menten equation. So this is the km of the Hill equation, k prime, it is k prime. So this is the Hill equation which describes this sigmoid kinetics. Now it's a little bit different, and we have two new things, this n. So what is this n? This n is called the Hill's coefficient. This n is called the Hill's coefficient. What is Hill's coefficient? This n will say whenever there is a positive cooperativity or increase in the enzymatic activity, the n will be greater than 1. The n will be greater than 1. It indicates that this is an allosteric activator. When n will be lower than 1, it indicates that it's a negative regulator or an allosteric inhibitor that is acting on this sigmoid kinetics, and this allosteric inhibitor will somehow affect the Km and the Vmax of the reaction. We always know that Km is what? Km is equal to the substrate concentration at which half of maximum wave. Km is the substrate concentration at which half of Vmax is attained. Half of Vmax is attained. So if the Km is lowered, means the Km is lowered, say this is the Vmax, and this is half of maximum velocity, this point. So this if this is half of maximum velocity, so this is the substrate concentration at which half of maximum velocity is attained. So this substrate concentration is the Km of the reaction. So when the Km is lowered, say this here, if the curve shifts to the left of this curve, the Km is lowered. That means when the Km value is lowered, we know that the affinity has increased. When the Km value increases, say this sigmoid kinetics is now here, is now like this, the Km value increases, and this means that there is a negative kind of regulation. There is a allosteric inhibitor that is acting. When the Km value increases, it's a kind of inhibition. When the Km value decreases, it's a kind of stimulation. That is Km value indicates, the Km actually indicates the binding affinity. When the Km value increases, that is at to reach half of maximum velocity, to reach half of maximum velocity, you need lower substrate concentration. With the Km value decreases, means to reach half of maximum velocity, you need lower substrate concentration. That means the affinity has increased. When the Km value increases, to reach half of maximum velocity, you need more substrates. That is, Km value has increased. That means affinity of the enzyme towards its substrate, has lowered. Now this how will we see this? Now let us observe this Hill equation. This V0 equal to Vmax into s to the power n by k prime plus s to the power n, and let's convert this equation into we will convert this equation into a equation of a straight line. And how do we do it? We just do a little bit of juggling into this reaction. And what is the juggling? We write this equation like this: Vmax by V0, that means Vmax by V0 is equal to k prime plus s to the power n. This factor goes up by s to the power n. Initially I can just put down Vmax here. I rub out Vmax from here. So V0 by Vmax is equal to s to the power n by k prime plus s to the power n. Just reversing reciprocating this thing, it becomes Vmax by V0 equal to k prime plus s to the power n. This factor goes up by s to the power n. Now we just subtract the lower component, the denominator from the numerator Vmax minus V0 by V0, and in this portion also we do the same, k prime plus s to the power n minus k prime plus s to the power n minus s to the power n, k prime plus s to the power n minus s to the power n, just like this. Vmax minus V0, here is this is the numerator. The numerator becomes Vmax minus V0 by V0, and to the right hand side we also have to do that function k prime plus s to the power n minus s to the power n by s to the power n. So s to the power n cancels out, and so what remains, Vmax minus V0 by V0 equal to k prime plus s to the power n, k prime by s to the power n, by s to the power n here cancels out. So now if we take log here, log here, log and log here, both side, so it becomes log of V0, and just inverse the equation, log of V0 by Vmax by V0, log of V0 by Vmax minus V0 equal to n log s, n comes forward, n log s minus, because this reaction has reversed, so the analog is below, so it is minus log k prime. So this equation becomes a equation of a straight line where log V0 by Vmax minus V0 is equal to y, n log s, n is basically the slope of the reaction, m of mx plus c, y equal to mx plus c, n becomes the slope of the reaction, log s is the x of the reaction, and minus log k is the c of the reaction. This is transforming the sigmoid kinetics to a straight line. Now if we see, if we always know that V0, if we know that at Km V0 equal to half Vmax, so we always know this condition that at Km V0 is equal to half Vmax, velocity is equal to half Vmax. So Km is the subset concentration at which half of maximum velocity is attained. We always know that. So at Km it is V0 equal to half Vmax. So if we plot, if we write V0 as half Vmax, so here if we write half Vmax instead of V0, and here also write Vmax by 2, so Vmax, half Vmax by half Vmax, so Vmax minus Vmax by 2 is equal to half Vmax, so Vmax goes out, it becomes log 1, which is 0. The value of log 1 is equal to 0. So we can say that this is the y-axis, this log factor makes a y-axis. So if we plot this log of V0 y, Vmax minus V0 is the y-axis, and log s is the x-axis, So at this plot, in this plot, the zero value means at half Vmax, the zero value of y-axis gives the value of y-axis gives the value of log s. So any straight line is formed, say this is the straight line, and this is the zero value of y-axis gives the value of log s, that is the Km, and from here we can know the Km of the reaction. So this is the significance. Why do we transform this sigmoid kinetics into the linear form? To obtain the Km. And why do we get that? Because the zero value of the y-axis, if we have a straight line, we always have a zero value of the y-axis, and that zero value of the y-axis plots to the Km, the log s value, and this log s value is basically the Km. So this is all about the sigmoid kinetics, the Hill equation and the derivation of the Hill equation, to a linear transformation of the Hill equation to obtain the value of Km. The value of Km is basically a subset concentration at which half of maximum velocity is attained, and that value we can get it from this linear transformation. So I'll quickly revise what is allosteric modulation, whatever we have read. So what is allosteric modulation? I'll revise the properties. So allosteric modulation, by allosteric modulation we know that, by now that we know that in allosteric modulation what happens, specific ligands or specific substrates or specific inhibitors or regulators, the specific low molecular weight ligands or specific regulators bind to specific sites of enzymes, affecting the enzyme action either positively or negatively. If it is allosteric activator, it will stimulate the Vmax, it will lower the Km value. If it is an allosteric inhibitor, it will increase the Vmax, it will increase the velocity, it will lower the Km value. If it is an inhibitor, it will decrease the velocity, and it will increase the Km value, it will lower the affinity of the enzyme. So the second point is, first point is the specific low molecular weight ligands or the allosteric modulators will bind to the enzyme, affecting the enzyme either positively or negatively. The second point is allosteric sites are different from the substrate binding sites. These allosteric modulators will bind to the enzyme. These allosteric modulators will bind to the enzyme at a particular site which is different from the substrate binding site. And this I have given an example. Say aspartate transcarbamylase. Aspartate transcarbamylase, when treated with mercurials, mercurials, a specific group of chemicals containing mercury. This aspartate transcarbamylase, when treated with mercurials, these mercurials affects its allosteric sites. These mercurials affects the allosteric sites of the aspartate transcarbamylase, and so the allosteric inhibition, the allosteric inhibition of the CTP. CTP is a product of this aspartate transcarbamylase reaction pathway. It is the final product. CTP actually inhibits aspartate transcarbamylase, but this inhibition goes away. When this aspartate transcarbamylase is treated with mercurials. But when the inhibition goes away, the allosteric inhibition goes away, it does not mean that the enzyme activity goes away. The enzyme activity do not go away. So by this we can know that the allosteric inhibition is a separate part of an enzymic behavior, and the enzymic action resides in a different part of the enzyme. The enzymic actions, how the enzyme acts. So if it is like I'm writing with my hand, but I am eating with my mouth. So if I'm doing a function with one side, my hands, doing something on my hands will not affect my mouth. So they are different sites, these allosteric binding sites which acts on the enzyme. So this mercurials has differentiated, these chemicals has differentiated. CTP was originally able to bind this aspartate transcarbamylase and inhibit the enzyme, but with these mercurials binding to this aspartate transcarbamylase rendered this aspartate transcarbamylase ineffective for the CTP. CTP will no longer inhibit this aspartate transcarbamylase, and this aspartate transcarbamylase, what will it can still act on its substrate. But the inhibition goes away. So by this we can say that allosteric sites are different from the substrate binding sites. And the third point is, these allosteric sites are separate. They can be one or more allosteric sites binding to one or more activators or inhibitors. So there can be, these allosteric sites are separate, that we have learned it from this point. These allosteric sites can be one or more, and they may be inhibitors binding to this enzyme and inhibiting the enzyme, at the same time activators binding to the enzyme and stimulating the enzyme. The third point is, effectors may affect binding. While binding, it will increase the Km value. It may affect the binding of the substrate towards the enzyme. any enzymatic reaction primarily requires one thing, very important thing, that the inhibitor or the substrate should bind. Everything should bind to the enzyme. So if an allosteric activator or an inhibitor affects the binding of the enzyme substrate, say it affects the binding of the enzyme substrate, if it affects the binding, so it will affect the Km. But if it affects the catalysis, so it will affect, if it affects the catalysis, if it affects the way the enzyme acts on the substrate, how fast if it affects the velocity, it will change the Vmax, the velocity or the Vmax of the reaction. So effectors may change the Km. So these kind of effectors which changes the Km are called K series effectors. K series of allosteric enzymes. So there are different examples of K series of allosteric enzymes, examples of M series of allosteric enzymes, where M series are where Vmax is affected. It is the K series and the M series. The Vmax, so those modulators which change the Vmax of the reaction belong to the M series. Those modulators which change the Km of the reaction, the Km of the enzyme, are the K series effectors. Now there can be another new point, which is homotropic as well as heterotropic. So homotropic and heterotropic, what does this two word means? Homotropic means the substrates are affecting the reaction. Homotropic means it is nobody else. The substrate are acting on the enzyme to stimulate the enzyme. So that type of activation or inhibition is called homotropic activation. If it is any molecule which is different from the substrate, it is heterotropic. Examples of heterotropic are aspartate transcarbamylase, ATC, and PFK1. These enzymes can be affected heterotropically by different other molecules other than the substrate. Examples of homotropic is acetyl-CoA carboxylase, where the substrate can stimulate or inhibit the enzyme. And K series, there I'll go to the next point. The allosteric, what are the properties of allosteric enzymes? It obeys the Hill sigmoid kinetics. Hill sigmoid kinetics, just now I told you, it is kind of S-shaped curve. It is the S-shaped curve, and not the hyperbolic curve. Then so this is the allosteric enzymes follow the Hill sigmoid kinetics. And there are feedback allosteric inhibitions. What does that mean? Feedback means, say a reaction gets converted from A to B to C to D, and this is a pathway, and say there are enzymes X, Y, Z. So this is the pathway and this is the product. This is the primary feed of this pathway and this is the product of the pathway. So if this product inhibits any enzyme here, it is called feedback inhibition. So allosteric enzymes have feedback allosteric inhibitions, means a metabolite of a metabolite later in the pathway, say D is the metabolite later or the product of the pathway, inhibits the earlier enzymes of the pathway. So this is called feedback allosteric inhibition. There are examples of feed forward allosteric activations also. What is a feed forward allosteric activation? Say feed forward allosteric activation, say B is stimulating Z. Z is an enzyme and B is stimulating Z to convert anything that B has converted. Say C is the product of Y acting on B. Y is the enzyme which has acted on B to produce C. Now to ensure that C gets converted to D, B is stimulating Z it is a feed forward activation. B stimulating Y, it can also happen this way, B stimulating Y. That generally happens in an enzymatic pathway. Substrates stimulate the enzyme, but it can. But in a later reaction, in a pathway where in the later part of the pathway, these substrate molecules can also feed forward, in a feed forward way, it can stimulate the enzymes, and these are the examples of feed forward allosteric activation. So here feed forward allosteric activation example I have given: fructose 1,6-bisphosphate, a glycolytic metabolite, will stimulate pyruvate kinase later in the pathway. Pyruvate kinase is present later in the pathway in glycolysis, and it will stimulate pyruvate kinase to take away the phosphates from the enol pyruvates and form pyruvate molecules in the glycolytic pathway. So fructose 1,6-bisphosphate is a earlier is a metabolite, is like B. It is a metabolite earlier in the pathway, and this fructose 1,6-bisphosphate stimulating Z, which is say pyruvate kinase, so that phosphoenol pyruvate gets converted to pyruvate. So these are the just to revise. So what are the very important points of allosteric modulation? They are affected by low molecular weight ligands. These allosteric sites are different from the catalytic site, and they are different from the substrate binding sites. They are different. These allosteric modulators bind at different points in the enzyme to regulate that. So this was this point. The third point is there can be numerous one or more allosteric inhibitors or activators acting on the same enzyme. The fourth point is the effectors may bind or influence the km of the reaction, or it can influence the catalysis. That means it can influence the Vmax of the reaction. The fifth point is the inhibitors, when these inhibitors or activators are actually substrates, this is called homotropic allosteric. When it is other than the substrate, it is called heterotropic allosteric inhibition. The fifth point is the allosteric inhibitors will the allosteric enzymes will follow sigmoid kinetics of Hill, and it is given by the Hill equation. Hill equation is the velocity is given in Hill equation. The velocity is given by Vmax into s to the power n by k prime plus s to the power n. So that was Hill equation that you have to remember. And the fifth point is these allosteric inhibition and stimulation can feed forwardly activate or feedback inhibit an enzyme. So these are the properties of allosteric regulation. 1, 2, 3, 4, 5, 6, 7. These 7 properties you have to remember for while you study allosteric regulation. Thank you.